Imagine a robot that learns a new skill, then another and another. The challenge? It often forgets the old skills as it learns new ones. This is called catastrophic forgetting. Traditional solutions often require storing old demonstrations, which is becoming impractical. We need a way for robots to continually learn without needing to keep all their past experiences in memory. The key to our solution lies in World Action Models, or WAMs. Unlike older robot policies that just predict actions, WAMs are powerful generative models. They unify perception, prediction, and control, and crucially, they can generate future visual observations of the scene. This means a WAM can imagine what the world would look like if it performed certain actions. This paper introduces RAGEN, or Recurrent Generative Replay, which leverages WAM's generative power. Instead of storing actual past demonstrations, RAGEN uses the WAM itself to hallucinate or synthesize pseudo-demonstrations for previously learned tasks. When a robot learns a new task, RAGEN generates these imagined replays of old tasks, allowing the robot to rehearse them and prevent forgetting. This diagram illustrates the core idea. Let's break down how RAGEN generates these pseudo-trajectories. It starts by conditioning the WAM on prior task instructions and an initial real observation from the new task. Then, in a recurrent loop, the WAM predicts an action and a future observation. This generated observation is fed back as the input for the next step, creating a complete synthetic trajectory. This process continues until the task is predicted to be complete, effectively imagining a full demonstration. We evaluated RAGEN in both simulated and real-world manipulation tasks. The results show that RAGEN significantly reduces catastrophic forgetting. Compared to sequential fine-tuning, which forgets nearly everything, RAGEN reduces forgetting by over 50%. While it doesn't quite match the performance of methods that have privileged access to real replay data, it comes remarkably close without needing to store any actual demonstrations. This table summarizes the performance across different benchmarks. Despite its success, RAGEN has limitations, primarily stemming from the generative fidelity of current WAMs. We observed two main bottlenecks. First, visual degradation, where generated observations become blurry or artifact-ridden over long horizons. Second, an inconsistency between predicted observations and actions. The WAM might imagine a successful outcome, but the actions it generates might not be physically sufficient to achieve that outcome in a simulator. This figure illustrates these issues. In conclusion, RAGEN is a significant step towards continual robot learning without the burden of storing past data. By enabling WAMs to generate their own replay, we've shown a practical way to mitigate catastrophic forgetting. Addressing the identified limitations in WAM's generative fidelity and action observation consistency will be crucial for future advancements. This work establishes WAMs as a powerful foundation for robots that can truly learn throughout their lifetime.